All right, welcome back, Red Eyes members. We are talking to physicist Holger B.Nielsen from the Niels Bohr Institute. We're talking about some, in some cases, complex issues, but also very interesting issues in terms of the Large Hadron Collider. We're talking about their model, basically some of the things that they expect to happen when it comes to the LHC down at CERN. And I guess one thing that I would like to clarify a little bit more here at the beginning of this segment, Holger, is basically what you expect to happen now then when the LHC is expected to start up in February. I don't know if the full power will be on, as you mentioned before. They will be running it on half speed or less or so. But what do you expect to happen? Do you think there will be any radical new discoveries made right away, or will it take a little bit of a time for them before they get it up and running?
I think it will take some time before making two radical discoveries, because most of the things one could hope to discover, that is the things where you really use the high energy by making hard collision, that one little particle in the one proton hits a little particle in the other proton, and then they make a big collision. Because what really happens in these machines which shoot with hadrons, of which the hadron is basically the proton, this proton is in the modern theory composed of quarks and gluons to some extent. Mm-hmm. And these constituents, quarks and gluons, this means that we should really rather think of the proton as a little swarm of particles. Many particles are there. And these particles that are there, they are very small, but the proton itself has a length of has a size of the order of 1 Fermi, which is very small on a human scale, but which is somehow big on the scale of distances relevant for LHC. Mm. So, in a way, you are shooting two swarms of quarks and other particles, gluons, against each other. And these particles in the swarm, they are sometimes called partons, mm-hmm. by the name of Joachim. These partons now sometimes hit each other closer or with higher energy in the collision, but very often the partons go by each other and they are only disturbed a little, and most of what happens is that you get some more hadrons produced, but they are produced with rather small momenta perpendicular to the direction of the beams, but so they are mainly following the beams. The beams are going head-on, we can imagine. Mm-hmm. And then these partons are going only little to the sides, with only small energy to the side, most of them. And this is a typical type of events. But the interesting events, where you really make use of the high energy, those are the ones where these partons collide with so hard collision that some partons, and they then convert into hadrons, but it doesn't matter, that you get some bunches of energy and momentum going on the direction not parallel to the beam, but out to the side, so to speak, transversely. And these events are more seldom. And the events where you really get very hard shots and can see the interesting physics which should come, where you really make use of the high energy of the parton, those are more and more seldom the more high energy you require. And if you, for instance, want to produce Higgses, then you have to wait relatively long and select your event. So in order to do it, you run the machine at so high intensity that you get a lot of uninteresting events, and then can select a few where there is a chance to see something interesting. And among those, you might find a very, very few where you really have a Higgs produced. So in order to get, for instance, the Higgs, which would be one of the interesting things, you have to run the machine so that you produce a lot of particles, a lot of collisions, and a lot of the uninteresting, and then some interesting, and then finally some Higgses. And this will take that at least you bring the machine up to run with the full speed, with the full, all the 3,000 bunches around the machine should be full at least. But I think they will do that in February. Mm-hmm. So then you will begin to be able. But it depends on how high intensity, how many protons you have in the beam. And if you don't, if you only do it on a low rate, then your chance of finding is even longer out in time. But even with high rate, you have to wait quite a time before you really see enough Higgs particles that you can say definitely that you saw it.
Yeah.
Because there's a lot of so-called background, which means there are a lot of particles, there are a lot of events that look a little bit like, could this be a Higgs? Maybe, yes. But you have to find out that really you have too many of the type of events that look like having found the Higgs, and then finally you may be able to say convincingly, statistically, that you found the Higgs.
Huh.
But it takes a lot of time.
And
it depends on the mass of the Higgs a bit.
Yes, I think, should we clarify as well that all of this is I guess, recorded, if you will, by the detector, the Atlas detector, and do you know if this is like it captures the events in a very high...
It does, but not really, because the point is that the electronics and the computer setup and so on for studying these events and storing the data is so that you have decided or cannot afford to store all the events. But as I told, most of the events are not very interesting.
Yeah.
It's mainly the ones with some particles going with big momentum transverse to the beam that are most interesting. And therefore, you have some trigger system called that you select which events you want to write down. So the computer or some special trigger system, which is a kind of computer system, there are several layers of trigger even, they determine what they want to store and for how long, so to speak. And the things that the events you really store is 1 in a million or so. So you run with this computer under the normal conditions something that you get about 1 million events. And then you take one. But this goes very fast.
Yes.
So it takes a lot of events already in a second and so on. But many events, the whole thing goes with very high speed. And you fill, even after doing it that way, you fill telephone books amount of data. So you have so many data that you send them out on a big grid all over the Earth to various stations around the Earth which collaborate electronically, computers that collaborate in a so-called grid in order to analyze the data which come out. But this days it's only 1 in a million, roughly, of the data you take up in the instruments that makes the measurement in the first place.
Yes. I mean, we're talking about 40 million times per second collisions taking place and things like this.
Yes, that's right.
I mean, that's incredible amounts. So I know that CERN was one of the institutes, I guess we can call them, who first developed the internet as well, because they wanted to link up computers and things like this. And is this what you're describing here as well, that there's a kind of a link-up taking place between different computers?
Yes,